Yeah, we have the homework due today. Posted new homework. Probably a few hours from today will be the new homework. So homework 1 was due today. Homework 2. Say, made it yet. So tentatively 27th, let's say. This is tentative. Next. Thursday. Depends on what kind of questions. Okay. So we had our Maxwell's equations. We broadly talked about electrostatics and magnetostatics. Now let's bring back all our equations at one place and write them as Q is equal to charge density. Everything is both position and time dependent. We have cross E equal to minus this as H equal to it's good to write this as actually let's write this as D. J. Here the definitions we have used is C equal to epsilon naught times E and B that's our total Maxwell's equation. And we also have the Lorentz force. Here the idea is that you be the charge and current, it gives you the electric and magnetic field. And if you're given the electric and magnetic field, what's the force exerted on the charges is given by the Lorentz force. But now we want to understand what are the implications of these equations in general. We want to keep the time dependence. There's one thing that shows up very immediately, and that is, so the question is, what is the implication of this equation, right? So what can, so there's a consistency relations if all these equations are true, then this must be equal to that, and so on. So what can we talk about in that sense? So let's do the following. Let's take the time derivative of this equation and the gradient of this equation. So let's say, so let me start from this, or let me start from the fourth equation. So let's say 4, 3, 2, 1. So equation 4 implies, if that's true, I can take the divergence of that equation, and it's divergence of the curve, and that's the same as divergence plus that's the relation we get. If this is true, this has to be true. And what is this on the left hand side? That's an identity. The divergence of a curl of a vector. Think of an arbitrary vector. And what is that equal to on the left hand side? Any guesses?
Zero?
Yeah, it's 0. And why is that? That's fine.
And this is I mean, yes, this is a del cross H. Car means rotation. So
Yeah.
at every point, something coming into this point is equal to going out of this point. So that's why divergence of this car is
Exactly. That's a visual way of looking at it. That's correct. Like curl is always going in circles. You never have any radial. Yeah, and the divergence is in the radial direction that has to be there. So that's a good way of seeing it. Mathematically, we have one way to see this is, let's see. So it's good to sometimes see mathematically too. So we have divergence of a curve. It's something like this. So any vector in principle, it doesn't have the magnetic field. This is, let's use index notation. I think some of us like it. So this is a curl and that's a divergence, right? So this is del I of del cross H, ith component of that. Good. That's a way of doing this in index notation. And this itself can be written as, in terms of the Levi-Civita symbol, that's I, and this is J and K. So this is J, H, K. That should be good. So the ith component, sorry, this is a scalar, right? So it's a scalar, so there's no component also, it's a scalar quantity. Bring this in here. Epsilon I, so this is a number, right? It's either 1 or 0. If the derivatives don't affect it, so I can bring it out. So I'm going to do this in detail, but the basic idea is that if I were to do, there is an I and J here, and there is an I and J here, right? If I swap I and J, does this change? It's a derivative, like this could be d by like d1 d2, for example, right? That's equal to d by dx times d by dy. And if I were to swap it to 1, that's the same as d by dy and d by dx. Now the question is that the two the same? Like, often not, but we deal with functions where this doesn't matter. In fact, if these two are not the same on functions, then it's not integral. You cannot integrate them in a two-dimensional plane. Right? It's like the conservative force that you have in thermodynamics, for example. When you have a reversible process, you go along this and you don't come back. That's because this doesn't work there. But if that is true, then you can do that. And we work with functions where that's possible. So these two are symmetric. So if I swap these two, it doesn't matter. It doesn't change. But if I swap these two, it changes signs. So one is symmetric, one is not symmetric. They cannot get along together. They have to be zero. But let's see this more explicitly. That's in very geometric way or in a logical manner I was trying to do. But let's try to use this argument to show that this is actually zero. So I want to use that feature, right? So what I'll do is, let's say, this is epsilon ijk, right? And this is equal to half of, so let's say 1/2 of del I, del j, plus del j, del I of h of k. Why? Because just now whatever I said, right? If I swap things, doesn't matter. So these two should be the same. So I divide it by 2. So that's good. But now let me write that as two explicit terms. So it's epsilon I j k I j k and plus 2 epsilon I k that seems to be almost an identity there, right? We didn't do much. But now let's do the following. I can bring this back to this form by relabeling my j and I. This is a dummy. So I'm going to call j i's and i's as j's. I'll do the same thing here. I'll replace j with I. J. Is that clear what I did? Right. I swapped my indices. It should not matter because they're dummy, right? So that's the same as 1/2 epsilon I j k I j k and now plus half of epsilon j I k I j. And now this is in the same form. So I can do 1/2 of epsilon I j k plus epsilon j k. This is the same. Great. Yes.
Do you need a minus sign?
Not yet, right?
Okay, so you can switch the J and I's.
I did not really switch. What I did is that
Oh, I see, I see.
I just renamed them. Like these are dummy. So wherever there is an I will call it a J. Wherever there's a J, I'll call it I. So since they're dummy, it doesn't matter. Is that clear? So I haven't really swapped them. They seem like they have swapped. But I'll now do the swapping at this point. Like I haven't yet used the anti-symmetry property. What I've done is that I've used a symmetry property and I'm seeing how does it affect this tensor due to that symmetrization. This is called the symmetrization of a tensor. So I've used that symmetry property and now how does that affect this? Now it shows up like this. But here I know that this is antisymmetric. So if I swap this down, this changes sign. So this is equal to 1/2 of epsilon I j k minus epsilon I j k times del I. That's where I use antisymmetry. And the moment I do that, oh, this is 0. This is identically 0. That's it. So I use the symmetric property of part of the tensor. How does it affect the antisymmetry part? And together they cannot relate. I could have started with antisymmetry part, showed that oh, these were the same, and taken it there on the other side, and that could have been another way of doing it. So that's an explicit mechanical way of doing it. But whatever you guys were telling that the curl, that's also okay. But sometimes if you're not very clear about the geometric thought, sometimes you might be confused or you may not be convinced completely that that's the case. This is a more brute force method. Good. So that's equal to 0, right? So we said if Maxwell's equations are correct, then this should be, this statement should be right. And we in fact learned that this is equal to 0. Right? So this tells us that this is equal to 0. And that's equal to, let me again, like partial derivatives of x and y, they can be interchanged. Time and position also can be interchanged. These are partial derivatives. So I can change derivative, time derivative of the divergence of t plus divergence of current density is equal to 0. So that's just using 4, right? And or there's a constraint in 4. But now bring in 1, like there has to be consistency between them. So use 5 or use 1 actually. Use 1 inside this equation. That's just rho. Right? So what you learn is that the time derivative of charge density plus the divergence of the current density, that's equal to 0. And this is often stated as the conservation of charge equation. Often we say in electricity and magnetism that charge is conserved. So in what sense is it conserved? So this equation has a conservation property. So this is called conservation of charge. So let's see what this means as such. So there's a meaning associated to a generic equation of this kind. So let's say so this is sometimes also called in fluid dynamics, it's called the continuity equation. Is that familiar, continuity equation? Okay, so let's see what this means. So let's change context, like a different context, okay? So this is writing it so that it's not confusing that this is the same thing I'm doing. It's a different context. That means that I'm going to use the same rho and j, but that doesn't mean it is charge density and current density. Something else, some parameter else. So let's say time derivative of rho, right? And it has position and time dependence, plus the divergence of j, it is, we'll call it current density again, plus let's say it's not equal to 0 instead. It is some s, it's a scalar, or t. is equal to 0. We would like to have an interpretation of what this means. So let me again, in short, write d rho by dt plus the divergence of J plus S is equal to 0. So I want to give a meaning to this equation. In what sense is this a conservation equation? So that's what we want to do is we want to integrate. So this is a local statement, right? Local in the sense that this equation is true at R and T. At every position and time, this equation is true. Derivative at a certain point in time and space.
You added the S arbitrarily. Yes.
Why did I go from here to there?
I mean, no. This S, R and T, S.
Yeah, this is a function of R and T.
Why do you add the S? I mean.
Oh, why did I'll give a, that's what I'm trying to come at. So this is some random equation, let's say. At this point, in a different context, there is an equation, let's say, which we have, and I'm going to give it some meaning in a moment. Okay. So, so let's to get the meaning clear. So let us say we integrate over a fixed volume. So that's yeah. Right. So let's integrate over a fixed volume. So this is true for at any point. So let's say this is a volume. So this is the volume. And when I have a volume that has a surface, right? S will be the surface. S stands for surface. And V will be for a volume. Okay. Let me integrate over volume everywhere. So that will be d cube R on this volume V. And then we have rho over dt and plus, everyone is switching off, right? And plus d cube R V divergence J plus d cube R on the volume V F, that's equal to 0. Clear? Again, this is a volume integral. I can move it in and out of the time derivative unless this volume itself is time dependent. That they keep it static. We're not going to move the volume itself. So move this out, and I have time derivative of a volume integral of rho. Again, nothing wrong in thinking of this as a charge density. The integral of charge is integral of charge density is charge. It's a time derivative of charge. So nothing wrong in thinking like that, but keep pushing on. What is this equal to? A volume integral of a divergence. That is a mathematical relation in vector calculus.
Pointer.
Huh?
Pointer.
Pointer, if that was an electric field, you're correct. And like if this was an electric field, you're right, absolutely right, that this will give you the point charge out of that. But in general, this is divergence theorem, right? If you have a divergence over a volume, it is the same as the surface integral of the field itself. So this is the same as instead of volume integral, you do a surface integral, but closed surface integral. You gotta capture the whole surface. Okay, so dA dotted with J, and again you have a volume integral of S. Is equal to 0. Okay.
S is the surface function,
S is the surface.
or is it? It's not related.
Yeah, this two are. Yeah, allow me to. This is a small s. It's a capital S. Right. Let me live with that. Okay, I think this is surface. That's source. So here, this is the source. There's a specific reason why I call it a source. That will be clear in a minute. Few minutes. Right. So. Okay. Any questions as of now? Okay. So let me give it now some definition here. So let's say. So let's shall I call this a source? Yeah. Yeah. So let's say this is Q. Of course, that means charge, but I'm going to not interpret it as that just because there is a source. So this I'm going to say, yeah. So this is a country, okay, and this has a boundary, and we want to investigate what decides the population of the country. Okay. So this is going to be the population of it. So as a population density, if you integrate over volume, think of it as a three-dimensional country, right? There's lots of skyscrapers, and that's a population of the country. It depends on where people are, and if you're given the population density, then you know okay. In that spirit, S times dA started with J. Now, what does this mean? Think of electric field integrated over an area A. Right? This is the flux. So this is the flux of the population. So let me say it's the flux of J is the flux. Two definitions here. Okay, that's so let's say this is a measure of population crossing the boundary of the volume B, boundary of volume. Is that clear? So if you have a lot of people in here, there is people leave the country and come into the country. It's like people crossing and immigration. Like some people immigrate, some people immigrate, and so on, right? And there could be death, and people are die and they are born, right? So S is the source. So birth or death rate. If source, if it is positive, it's an increase in population. If it's negative, it is a decrease in population. And we know clearly in this interpretation that the rate at which the population is changing, right, is equal to the source plus the rate at which the population is leaving the country. So together, all this has to balance to 0. So, plus integral is equal to 0. Is that clear? In charges, what is happening now? So now let's go to the charge. We learned in charges that d rho by dt plus del dot j is equal to 0. What that means is that you can actually, charges can go off the boundary. That will lead to a change in charge, but charges cannot be created or destroyed. That's because the third term is 0. So there's a big implication in here. That's why it's called conservation of charge. That this term doesn't exist in the Maxwell's equation. So you cannot create or destroy charges in the classical Maxwell's equation. There is no way to do that. And that's coming from this interpretation. Any questions here? And we will do more of these things, like we will talk about, so this is now conservation of charge. We'll talk about conservation of energy, conservation of momentum, conservation of angular momentum, similar things can come out of these things. Comments, questions? Yes.
We're still in the static case, right? Like the magnetostatics. Or where?
Tell this again.
Oh, we're still in the like static
No.
case.
No.
Okay.
So maybe your question is, so we're not in static case. That's the simple answer to your question. We're not in the static case. But then you can ask, how does this equation look like in the static case? In the static case, we will immediately say this is 0. Charge is not equal to, or charge doesn't move around, which means that gradient of divergence of current density is equal to 0. And we don't emphasize this so much when we are doing magnetostatics. In magnetostatics, the currents that we talk about, they have to be steady. Like they cannot actually come out of a point. So let me clarify that better. So this is a good point to raise. So let's look at magnetostatics. So magnetostatics would be divergence of B is equal to 0 and curl of H is equal to J. That's all there is to it. This would immediately imply that B is equal to del cross A, that exists a vector potential which gives you the magnetic field, right? But what about this? We can take the divergence of this. Left hand side is 0. This implies that J has to be equal to 0. Is that clear? And what does that mean? The statement usually in words is that the currents that we talk about in magnetostatics has to be steady. In what sense steady? So for example, I cannot have, again, what does this mean? That J does not have any source. Current density does not have any source. There should be no point where current density actually exists on its own. So that means to say that wherever you create a J, it has to end. So like you cannot just, there cannot be a source of J. That's not allowed. You have to finish it up. It has to come in and go. So that's okay. So you can have a loop of current. And if you're taking it, sometimes you take it all the way to infinity. Even that will have issues unless you kill the fields also reasonably fast at infinity. So it's necessary that all the loops go away, and often it also has to be steady. And you don't want to have it changing with time. Is that clear? And that's because of this like yes.
Field due to electric charge. Any field, electric field due to electric charge, and electric field due to a magnet, magnetic field. Does it behave differently?
Electric field due to a change in magnetic.
Yeah, change in magnetic field.
Yes, it will be different in the sense. So now, if you're in magnetostatics, you cannot produce an electric field. Correct. So, for example, let's see. What you're trying to ask is that. So let's consider del cross H, or yeah, del cross E. Right? So del cross E is equal to minus dB by dt. And notice that, so let's say this is kind of some source, right? Whatever this is creating the electric field. In electrostatics, curl of electric field is 0. That means that at every point, I can never have any electric field going around. On the other hand, if it is created with a magnetic field, I can have electric field going in circles. You never see this in electrostatics, correct? And it is possible if you recall your Faraday's law, right? If you have a magnetic field here like this, that is, you have a magnet, you bring this with some velocity, and you can generate an electric field, but they will always be in loops. So whatever electric field you produce using a magnet, by moving a magnet, it always has a curve. So they are usually circles. Like this always is in the form of a curve, not as a divergence. Electrostatics is produced by charges, just charges sitting.
Yeah, plus charges is outward.
Exactly. So that you can always, if an electric field represent electrostatic, you can trace it back and you will end up on a charge. If it is produced using a magnet, you can trace the electric field back and you will never end. You'll keep going in circles. So that's the answer to your question as to what's the difference between them. One you can trace and you will end up in a sink or a source.
So to actually produce a torque, I think that many times they use magnets, strong magnets to change in magnet and produce a strong electric field, circular electric field.
Torque in what sense? Torque on?
Actually means, circular, if I want to make a circular velocity, something like I want to turn something, a circular way, and I can use a magnet, strong magnet, and produce a electric field.
It depends what you want to rotate. If you want to rotate a loop of current, then a loop of current has a magnetic dipole moment, and then you use a magnet. Right? But if you want to rotate a dipole moment, electric dipole moment, right, then you will use an electric field. So probably you have something in mind, but you're probably not stating it. So,
we will try.
So, there must be some torque effect in here, which I'm not completely. Like that's the idea of a like Faraday effect is completely. This is Faraday effect, and this is very well used in a dynamo and a motor. Right? That was a revolution of 200 years back. Like these days, I typically say, these days we are living through a revolution called digital revolution, like which is really changing lifestyle, if you want. 200 years back, we had exactly similar case in electricity and magnetism when we started, we learned that this could create an electric field. So that was the idea of a motor. and a dynamo. And that was such a powerful idea that you get every day we had inventions coming up. That was an industrial revolution. These days it's a digital revolution, but one small idea leading to so many ideas that it's an explosion of ideas.
Is this principle used in particle accelerator?
No, there it is a cyclotron, right? I think you're having cyclotron in mind, where you create a magnetic field and bring it. So you use an oscillating electric field, and then it goes through a magnetic field. Probably yes, yeah, but not in the straightforward manner. Yeah. So look up cyclotron. I think that's what you're doing. Okay, so but I want to come back to this and stress on some features here. Basically, a nomenclature needs to be clarified here. So what I've introduced at this point is what is called a continuity equation in fluid dynamics. So let's say a continuity equation in fluid dynamics. So why are we talking about fluid dynamics when we are doing electricity and magnetism? But it has to do with the nomenclature. So give me a few minutes. Continuity equation in fluid dynamics is d by dt, exactly what we have there. Let's say q plus, or actually, let me not write it in that form, whatever we started it from there. So it is d rho over dt plus L started with j plus s is equal to 0. We of course defined those quantities a few minutes ago, but importantly, j is called, J is the flux. Notice the language. J is the flux of rho. And when you're thinking of a population, it makes sense you're talking about the flux of population. Flux is given an area, how many people are going around, and it seems to make sense, right? So that's the idea of flux in fluid dynamics in the continuity equation. That's a whole field, and they have a terminology called flux, and that's what they mean by flux. But now go to vector calculus, or which is what we use for electric field, right? So if you remember, we define the flux in electricity and magnetism, and this is some open surface S, doesn't have to be closed, times dA dotted with E. Correct? That's also flux. Right? That's a flux of the electric field. Right? So here, phi E is the flux of E, like the vector field E. Again, flux shows up. Right? And they have nothing to do with each other. Okay, they're two independent concepts in two different contexts. And that was perfectly fine as far as you're doing fluid dynamics, that's good. And you're doing vector calculus, that's good. But electrodynamics really have these two together. So it is confusing. It has to conflict with each other. Okay. So for example, I can do that integral there. Right? So I can talk about what about del dot J, right? What is, so in electrodynamics, let me take this. electrodynamics. We have the A dotted with J, right? So this would be the flux of J, right? In the vector calculus sense, right? What is this equal to? If you have current density, if J is the current density, you multiply by area, what do you get?
Surface current.
Surface current or just a current itself, right? I think it's a current itself, like if you have a tube, right? And there is this area there, and there is this J usually is in this direction. You're taking that area J, current per unit area is your J, right? So that's your I. It's usually in, if it's a constant surface, it's current per unit area is J. So that's your, and that's not the same as this, right? So there are two, like here, J is the flux of rho. Here, I is the flux of J. Both are different statements. Right? One is in the vector calculus sense. Current is the flux of J. Correct statement in the vector calculus context. J is the flux of rho. Correct statement in the fluid dynamics context. I'm not going to change this definition, whatever is there, but be aware of this. If there's two different definitions in two different contexts. For us, this is the important equation. I will keep tending to use this more importantly, even though we use this a lot in electrostatics, I will just try to not use this at all. So if I ever use flux, most probably it is this. And this is all there, but this is not important, at least in the context that we are in. We will try to get these equations. Whenever we have this equation, we will say J is the flux of rho in the sense of population, right? We want to talk about conservation equations, right? The flux of population that affects the population rate at which the population is changing. And that's what we are going to talk about. Okay. Any confusions or questions here? Okay, so that's your continuity equation. And now let's see if we can do other things with this. So let's go back, and we started with Maxwell's equations and manipulated and immediately got this equation. And we manipulate this again and get something else, right? That's what we will do. First, we will manipulate and get something in the context of energy, and then we'll go back and do something about momentum, right? So that will be our important. Okay. So the question we are going to ask is, is there a conservation of energy? Is that a conservation of energy statement? And then you go back and say that, okay, in Maxwell's equation, what do we mean by energy? Like we had charge density just now. Is there an energy density in Maxwell's equations? So what is the energy density? So let's call this energy density. Energy density. And That's energy per unit volume. And let's say that's U. What is energy density in Maxwell's equation? Do you remember from your think of introductory physics courses?
One by two CV square.
CV square, that's good actually, yeah. 1 by 2 CV square, right? That's correct, that's a capacitor, energy stored inside a capacitor, right? That's good, that's correct, okay? So if you have a positive charge here, and there's a negative charge, that's a capacitor, and inside a capacitor, what does this charges create? You have given me the expression in terms of C, which is a material property of this capacitor. But instead of that, go into in between the capacitor, there is electric field, right? You can actually convert this formula into the electric field, correct? C has, if it is parallel plates, it is 1 by 2 capacitance of a parallel plate is what? So capacitance is epsilon naught times area over distance, right? Over the distance, this, right? So it's epsilon naught times area over D, right? This is voltage across these two plates. Voltage, it can be written in terms of electric field, correct? So gradient of
ED.
Yeah, E times D, right? So it is E times D. It is CV squared, so it is E squared times E squared, correct? And one of the D cancels out. A times D is volume, right? So whatever this is total energy. That's energy. So if you see, there's energy per unit volume, right, which is A times D, is half epsilon naught E squared. Right. So if you have electric field anywhere, if you ever create an electric field, the square of the electric field is a measure, half of the square of the electric field is a measure of energy density. Right? Good. So that's a correct expression, except that this is given in terms of properties of the material, but perfectly fine. That's very good. So this is half. I can write epsilon naught times E as D, right? So this is conveniently written as D dotted with E. But that seems to be having electric field. What about magnetic field? Can you store energy in the magnetic field? Solenoid. Right? Solenoid has a magnetic field, and exactly the same way. So here, if you have a solenoid, correct? And if you have passing a current through it, you can actually generate magnetic fields in here. And you can again ask what is the inductance associated with this coil. And you can give it in terms of inductance of I times half L V squared, right? Half times L and then I dot square, right? Rate at which the current is changing. Right. That's your energy stored in there. But we are again interested in energy per unit volume, and that comes out to be half. The energy per unit volume is plus half B squared over mu naught. mu naught in the denominator. Take the mu naught to the numerator, replace d with mu times h, and this is also equal. So you can store energy in two ways. That's magnetic field or electric field. So at any point in space, if you create an electric field, this is just a square of the electric field, square of the magnetic field, you have energy density. You have energy density in the form of magnetic field also. And that's your energy density. Okay? That's the equivalent of what we said charge, right? If you have a population, we say at what rate is this energy changing? Right? Think of a volume, you have this, and now this can change. Right? And then we are to say what creates this energy. We would like to know what creates this energy. Clearly it's charges, right? Somehow charges has to come in. And can this energy go in and out of a surface? If you have an energy like we talked about charge can move around from given a volume, it can go in and out. Same thing you can say, so we can talk about what is the flux of energy density. What's the flux of energy density? Okay. So if you have a boundary, at what rate does it go across that boundary? What is that concept? Have you come across a concept called flux of energy? It surely has a direction, and that you have seen. This is called a pointing vector. It's called E crossed with H. So familiar? Pointing vector. That's the flux of energy density. This is also called. This is POYNT. Pointing. That's the name of a person. But very incidental that this should be along a direction, and his name also is. So it's called a pointing vector. And what creates the energy density, we have to now see what actually creates. It will be the charge density and the current density that will come in. But there must be a connection between all this. We would like to see what is the connection between this. This I just randomly gave you some concepts: energy density, flux of energy density. How is this related? And that has to be dictated by the Maxwell's equation. Currently, I just gave you two concepts which you have seen somewhere in physics before. But now let's try to derive these relations. And let's go. Okay, so let's begin with the idea of So what is power? Definition of power in physics: it's energy per unit time. Correct? The rate at which energy is dissipated is what that is. Energy per unit time. And if you think of this, energy is force times distance and divided by time. Distance by time, that's force divided with velocity. And force in the context of our electrostatics or in electrodynamics, this is charge times the electric field, right? So this is the same as Q times V times the electric field. Because force is Q times E. And you would say that, oh, there is a magnetic force also, right? But magnetic force is QV cross B. So when you dot it with V, that goes to 0. Right?
It is F dot V,
Uh-huh.
F equal to KV,
Uh-huh.
and then how the E goes to the right side.
Oh, because it doesn't matter, right?
Oh, yeah.
It doesn't matter. I just wrote it like that. Okay. And so that's power. But now let's talk about power density, right? Power per unit volume. Power per unit volume will be, right? So this is just and this is just a definition I'm giving just to motivate. That's QV over volume, right? Dotted with electric field. Q times V is nothing but current. Current per unit volume is current density. So this is nothing but J dotted with E. Okay. Which means to say that energy dissipation dissipated at a particular point. This is the source. Remember that if I'm sitting here and something is born, right, then that's a source of something. So here we're talking about energy born. Either you can dissipate or you can create energy. Right? That's decided by J dotted with E. So that's equal to J dotted with E. Right? Let me clarify that it's a position dependent quantity. So that's J R comma T dotted with electric field, which is R dotted with T. And there is no other term. You would have said, oh, what about the magnetic field? Oh, where is the magnetic field? Magnetic field doesn't do anything because there is a force here, which is perpendicular to velocity. It doesn't dissipate energy in the way electric field does. So there is no dissipation of energy as far as a Lorentz force equation. So let's begin with this. So let's start with J dot with A and see what we can conclude using Maxwell's equation. What is J dotted with E? Let's do some manipulations and learn something. That's J dot with E. What I'll do is, as much as possible, I want to get rid of all the sources and write everything in terms of electric field. So J, according to Maxwell's equation, is this, right? So let me put that in there. So that's del the curl of H minus the time derivative of the displacement field dotted with E. Right. There is no magnetic piece for this, but I'm doing manipulations here. So I'm going to multiply by 0. So what I'm going to do is I'm going to the space. So what I'm going to do is, I don't know whether it's plus or minus. Let me add, right? This is equal to del cross E and plus dV by dt. What is that equal to? That's 0, right? So I can always do that. I can add. For that matter, I could have also subtracted. So I don't know as of now whether I want to add or subtract. I'll decide in next step, right? In next few steps. That's 0, but that's a vector, right? There's a scalar I'm having. That's a vector. So I need to dot it. So I take the analogy here. I dotted with E and dotted with H. That's just adding a 0. Why not? And actually, I know what I want to do because this is negative. I want this also to be negative, so I'll keep the negatives. Like I want this structure to be the same as the negative of that. Okay. Okay, good. So let me put this together. Let me take this term and this term separately. So that's del cross of H dotted with E and minus of del cross of E dotted with H. And there is a time derivative. This is epsilon naught, right? Remember, and that is time derivative acts only on D, right? This is acting on D and then multiplied by E. So let me write that as epsilon naught of E dotted with dE by dt. That's what it is. I just moved it around. So that's okay. I can move E and D. And this one is minus of mu naught H dotted with time derivative of H. Right. Questions? There's something worrying. It's just this term I wrote this on the right side just because I thought nothing, no big deal. You can do it on this way. And I expanded D as epsilon E here, right? And let me keep the first two terms as it is. I'll process that later. Let's process the second and third term. E. Now that this is nothing but E dotted with a, so if you recall, V dotted with dV by dt is the same as E by dt of half velocity square, right? That's the kinetic energy comes like that, right? The derivative of velocity square is nothing but V dotted with V, right? That's the structure you're seeing here, right? So that means that this is a total derivative of half epsilon naught E square plus half mu naught H square. That's nothing but energy density. So we got the time derivative of energy density, right? Think of the flux continuity equation, time derivative of something plus the divergence of something. That's your source or sink, right? So that could be the energy statement. But first I need a divergence of, this is not a divergence, right? So I have to manipulate that a little bit, but it seems like I got the energy density to it. Correct. Just by manipulating this term started from here, use the Maxwell's equation, and then there is a zero we manipulate. That's what we find. Okay. This term, so let's process this. We know, I gave you a hint that there is a pointing vector, right? And the gradient of a point vector might do that. So let's, instead of doing this into that, let me actually try, what is this? I'll dot it with E crossed with H. What is that equal to? Okay, let's go back. So this is like we are a good index indices. Let's say this is I, and then there is epsilon I j k times ej k. Now this differentiation has to hit on the Levis-Civita, electric field, and the magnetic field. Levis-Civita is a constant, it doesn't hit. So it can hit on this or that. That's equal to when it hits on E, I'll write this as del I j times h of k. And when it, so this is a distribution going on, right? So that's epsilon I j k and ej times del I h of k. That's nothing but del cross E times H. So this is, bring it back, that's del cross E dotted with H. And this one is del cross H, but for that I have to switch my J and I, right? I have to use a negative sign there. So this is E dotted with del cross H. Which, when you compare with the top, oh wow, that's exactly the same thing, except that signs are flipped. Right? This is the negative sign, that's with the positive sign, that's perfectly fine. So it seems like we have an equation which reads, it seems like our equation reads J dotted with E is equal to, this term comes with a negative sign in there, so it is negative of E crossed with H and as a minus E by dt of U. So U was what we defined earlier. So we have a statement here, write it in the continuity equation kind of expression. Change in some quantity, here energy density plus. This time let me call it S. That's just because it's there's another S that is coming up earlier we used, but that was a scalar. And plus J dot with E is equal to 0. Where the definitions are U is equal to half E dot with E half D dot with H. That's energy density. S is going to be E crossed with H. And this is the flux of energy density. Which is also the Poynting vector. Like in radiation, say, oh, Poynting vector, how much energy goes out of the globe. That's the interpretation. And J dotted with E is okay, you changed your energy so much energy went away. What about the remaining? So either they died or they were born, right? So that's defined as energy dissipation. This is energy dissipation. That means birth or source or sink of energy. Energy dissipation. Or energy dissipated into charges. Where do you lose energy? Into charges. Like the electric field, the energy that was stored in electric field is being converted into motion of charges. The charge starts moving, right? The energy associated with that, the mechanical energy associated with the motion is where the electric, so energy can disappear from electric and magnetic field and get into the motion of charge. That's the and this will play a very important role when we are doing radiation. We will be able to calculate electric and magnetic field by solving for equations, but eventually we want to know how much energy is out there, and we will use this exact equation and say, oh, there's a flux of energy that goes in, and that's the final result. So that's a good place to stop, and we will, radiation of course will involve these expressions, but before that we can even do some simple expressions. For example, if there is an electric field that's hitting on a conductor continuously, can it push on it? Can you exert a force on a surface using electric field? Yes, in principle, when it's a charge, yes. But if it's a conductor, how does it work? So what's our understanding here? So we will try to have a similar equation for momentum, and that will be the idea of force. So we have introduced the idea of energy here and the flux of energy. Now we will do momentum and the flux of momentum will also. And there will be homework I'll post in few hours probably. It will be due at least in a week or a little more. Clear? Okay, sure.
For this material, are you following any particular chapters?
Yes, there is this book by Schwinger in my on the web page. I put it. It is Schwinger, Schwinger, Milton, Dirac, and Sykes. These are basically lecture notes of Schwinger, and they were compiled by Milton and his three of his postdocs about 30, 40 years back. And this is from the third chapter of that book. The third chapter. So it was an undergraduate textbook. He was teaching undergraduate, but usually you see these things at a very graduate level at the second semester of this year. We will do that. Yeah. But it is reasonably straight as of now. Conceptually, it seems okay. And the only challenge will be that in this way of looking at it, it's not very common to think of it as a pressure due to an electric field, momentum due to an electric field, how things move. It's not a very common way of interpretation, but very powerful. Very powerful. But it's well known, it's everywhere. Like if you want to look into Jackson, it's in chapter 8, I think. Like it's after special relativity there. I think it is chapter 8. Again, this is broadly called conservation principles in electrodynamics. That's a keyword. Conservation equations in electrodynamics. So first I derived the conservation of charge, and now this is the conservation of energy statement. So I'll proceed with that. Okay.